We're going to start this week. Narmada can tell us about geographical swings.
Okay. Hi, I'm a PhD student here, planetary student, and I'm going to talk about. The title of this talk is G delta local squaring. This is based on a recent paper with Spencer and Felix. And my goal for today is to try to outline some of the new ideas in the proof. And to do this, first, I'm going to tell you what we're proving. So what is the question we're trying to do? So some of you may or may not have heard of this already. In around 1925, Tarski posed his original circle squaring problem, where he said, if you take, I'm going to write this imprecisely now, and I'll write some more precise statements later. But if you take the disk of area 1 and the square of area 1, can you partition this into finite many pieces, and using just isometries go from the circle square. So these are functions that preserve distance, like rotations, translations, reflections. And a little bit of historical context. So this came right after the Varadarajan paradox, which is the more famous Tarski question, which says that in R3, or one version of this says in RK for K at least 3, one ball of measure 1 can turn into 2 balls of measure 1 using isometry. And the K, at least, before I get into some more precise mathematics, the K at least 3 here is very vital to their proof. It uses some facts about the group of isometries in 3 and higher dimensions that just fail in 2 dimensions. In fact, this Tarski paradox fails in 2 dimensions. So this was actually a non-trivial question for Tarski to ask. If we drop this paradox of measure, can we still have some weird things happen with isometries in terms of geometry? And so the precise definition hiding behind all of this is the definition of an FBD composition. So if we take 2 sets, A and B, in some dimensional space, we say A is FBD decomposable to be with isometries if I can partition A into finite many pieces. So this square cup means a disjoint union. And so there is a partition of A, and there are isometries, say F1 to Fn, so that when I apply these isometries to the pieces here, I get a partition of. So what the Tarski paradox says is actually something much stronger than this. What it says is if I take any 2 bounded sets in R to the K with non-empty interior, they're equidecomposable units. The bounded and the non-empty interior conditions are both kind of crucial here, but any 2 non-empty or any 2 bounded sets non-empty. And Tarski's question is the disk equidecomposable? And the techniques that were used to prove the Tarski paradox didn't work for this. So it wasn't until 65 years later, in the 90s, when a mathematician named Laksovich was able to answer this question. So spoiler alert, he said yes. And I'm just going to talk about more versions of circle squaring for the rest of this talk. But what Laskowitz proved was actually something much stronger than Tarski's original question. So I'm just going to give you the full theorem that he proved here. So if you have two sets in R to the k for k at least 2, and if we don't care about measure paradoxes anymore, so if they have the same positive Lebesgue measure, and I'll say R nice, because I don't want to go into it, but if you know the definition of box dimension or Minkowski dimension, what nice just means is that the upper box dimension of the boundary of A and the upper box dimension of the boundary of B are both strictly less than k. So they're not fractals, essentially, or not super bad fractals. So if they have the same positive measure and they're not super bad fractals, then and for shorthand here, I'll say A is equidecomposable B. So then A is equidecomposable to B with all the translations. So you don't need to use any other isometries except for translation. So, in particular, you can apply this to the circle and the square in R2, and you can do circle squaring with no rotations. You just partition the circle into some pieces and translate them to get the square. The more general.
Yeah, more general statement.
Yeah, Laskowitz has like a series of papers on like equidecomposability results, showing that these conditions are necessary, in some sense for this theorem to be true. Okay. So the question is, what do the pieces in this equidecomposition look like? So we have this partition of our circle into some finite many pieces that can just be translated to get a partition of the square. Can we hope to describe these pieces in any way? And this is where the descriptive and descriptive combination. Descriptive set. So to do that, I'm going to tell you what nice sets should be, and then we're going to see where our pieces are going to fit in some hierarchy of it. A different notion of nice. Yes, completely unrelated notion of nice. Okay, so this is the Borel hierarchy. So you might have seen Borel sets before. These are just sets that are countable unions, intersections, complements of open sets, or the sigma algebra generated by open sets. But we're going to stratify this a little further and ask how nice is the set in our collection of Borel sets. So we start like near the bottom with what I'll call sigma 0, 1. These are open sets. It's a sigma because it's closed under countable unions. And on the other hand, I have their complements, pi 0, 1. These are closed sets. And it's pi because it's closed under intersections, countable intersections. And in some very nice topological spaces, or I guess depending on how you like your topological spaces, we have the intersections of open and closed sets. These are the open sets. Okay, but if I want to build up now to get more Borel sets, I need to close this under countable intersections. So I get pi 0, 2. And I need to close this under countable unions. So I get sigma 0, 2. And then, so you might have also heard of these as G, did I get that right? I always forget which one is G delta. One of these is G delta. I believe it's this one. And F sigma. Yeah. And again, I take intersections, and in between the two of them sit something called delta 0, 2. And I, keep going, and this is a way to classify my Borel sets. Yeah.
What's this for?
Logic. Logic. Yeah, I can't answer that question in a satisfying way. but there are sigma 1, 2 sets and so on. Basically, continuous images. So if I take my Borel hierarchy and I look at analytic sets, if you've heard of them, these are continuous images of Borel sets, then I've moved one level like to the right. Yeah. And I can keep doing this. I can take continuous images of analytic sets and move another level to the right. Yeah. Okay, but we're not gonna go that far. We're gonna stay in the Borel hierarchy. And clearly the lower down a set is in the Borel hierarchy, the nicer it is. And not all Borel sets are going to live at some finite stage of this hierarchy. So it's not even clear that even if we can get Borel pieces, that they should live at a finite level here. But they do. And as you can probably tell, in fact, you can get G delta. So I'll state the general version of the main theorem, whose proof I'm going to study for you today. Actually, before I do that, I'll tell you a little bit about the history of Borel circle squaring, specifically for the circle of the square. So it wasn't clear for a long time that we could even do circle squaring in a constructive way, that we could hope for pieces that were Borel at all. And it wasn't until Marx and Spencer in 2017 proved that you can do Borel circle squaring, and in fact, you can do it with delta 0 for pieces. So going up to our levels here. The pieces are always going to live in one of these delta sets, just because whatever level of complexity they have, their complement also has the same level. And in 22, Martino and Piperno improved this to delta 3 pieces. And in 26, Spencer, Felix, and I improved this to delta 2 pieces. So this is something a little stronger than G delta. G delta has like the clickbait title, which is somehow worse than the actual proof, which is that these pieces are in fact delta 2. And our main theorem, so similar to how Laskovich has like the general version of this theorem for any two sets in R to the K. So if you have the same setup, you have two sets in R to the K, and this is also, similar. These previous works also didn't just prove circle squaring, they proved equity composability for sets A and B, where the complexity also depends on the complexity of A and B. The circle and the square just happen to be closed sets, so this is how the complexity works out. But the general statement that we have is that if you have two sets, K at least 2, and the same conditions there, with the same positive measure, and nice. Okay, so there's two ways I can say this. The first is that if A and B live in delta 0 alpha, or some alpha at least 2, then their pieces live in the same layer. So you don't need to go up any level of complexity to get an equity. I mean, delta 0 is a little more complicated than open sense. So I'm kind of lying to you a little bit. We do have to go up, but if you just care about these delta sets, when you're not going up at all in complexity, the full, statement is that A is equity composable to B with pieces that are, okay, it's a mouthful, so I'm going to say it and then I'll write it. They're countable unions of Boolean combinations of open sets and translates of A. So Boolean combinations of open sets lands you like here-ish, and then countable unions land you like, and then A and B can take you onward. And a Boolean combination is just a finite union intersection operation. Translate this combination. Any question about this statement? Okay, so there are a lot of different moving parts that go into reading this, and I don't have the time to go through all of them in detail. So my plan is to convince you that this is a graph theory problem, or that this is going to involve tools from graph theory. I'm not going to go into the details of how we use the graph theory to get an equity composition. This was done in the original paper by Marx and other, and the same method holds for the other papers. Instead, what I'm going to do is tell you about the kind of like improvements that we had to make to this technique to go from delta 0.4 to delta 0.2. Okay. You know, Latzkovich could also have done his original proof as a graph theory. So a lot of this is really due to his. He did?
Yeah. You check calls.
Yeah. But I guess he had a really good job.
Yeah.
But yeah, so where this graph comes from is actually from Latzkovich. So the first step is that it doesn't actually matter that the circle and the square have area exactly 1. They just need to have the same area. We're going to shrink everything to fit in 0, 1 to the k. And the reason I want to do this is because, so in 2 dimensions, I have a circle and a square here. And I just want to think about this as a torus. So I want to quotient out by the integers. We'll ask the same question for the torus, which is just, quotienting out by the integers, or if you just want to visualize it as staying within the square, that's fine too. Okay. And the translations have to come from somewhere, so we might as well just choose them randomly. And here, randomly is in the actual probabilistic sense of the word randomly, so choose D, where D is going to be approximately 2 times the dimension. Vectors, say x1, p, and I'll call this p k. Uniformly at random. And I'm going to look at all the translations these generate mod 1. So I'm looking at all possible integer combinations of these translations. Mod 1. So what that means is if I start here and start translating in this direction, as soon as I hit this wall, I bounce back to here and continue like this. This is kind of like, if you want like a 1-dimensional picture, this is exactly like taking the fractional parts of n alpha, where alpha is irrational. With probability 1, these are all very irrational vectors. And in fact, with probability 1, what you get is an action of z to the d on the torus that's free. With a free continuous action. And the way a graph shows up is essentially we take the Cayley graph, but like uncountably many. So what I mean by that is if I take the orbit of any point, or if I pick a point and look at all possible images I can get by applying my translations to that point, this is the orbit of that point. And I can, because it's a free action, I can identify it with a Cayley graph of z to the d. And if I do that for all of my points, I have uncountably many Cayley graphs of z to the d. This is called the Schreier graph. So to have a Cayley graph, you have to choose a generating set, and our generating set for z to the d is going to be a little different from the usual one. So it's going to be all vectors in z to the d whose suit norm is equal to 1. So if you think of how we usually draw, for example, z2, you would, have your vertical edges and your horizontal edges. But with this generating set, we also have our diagonal edges. It just makes some computations work out easier. The proof would still work with a different generating set, but this just is nicer for. Okay, so I'll so the Schreier graph is to actually write down the definition. So G has, so the vertex set is going to be the entire torus, and xy is an edge of G if x equal to n acting on y for some n in S. So this graph fits in kind of a skewed way on the torus, right? First of all, it has twice the dimension. So there's like a 4-dimensional grid on this torus at some random, literally random angle. I think there are just uncountably many copies of that. Okay. And the other thing that happens is that the points of A and B are now distributed in some way in this graph. And this distribution is essentially what the niceness condition about the boundary is. If you know about the Minkowski dimension, it is actually telling you how points are distributed in the grid. So let me draw another picture over here. So again, here we have the circle and the square. And if we pick a point in the circle and start moving it, maybe at some point we hit something in the square. So if we look at what that looks like in our graph, we have something like, the path going from a point of our circle to a point of the circle, right? And this path, this path corresponds to a translation, right? I translated by the first vector in this direction and the second vector in this direction. So the idea is that paths in G are, translations. And if I want to send the circle to the square using only finitely many translations, then I want to use only finitely many types of paths. So specifically, what I'll say is finding, bounded distance. So there's a uniform bound on the distance paths from the circle to the square, or the more general setup from A to B in our graph G is the same as finding an equity composition from A to B. And we just need to find a way to send vertices of A to vertices of B in the graph. This is sort of like a perfect matching, but a little worse. because the vertices might not conjugate. And the thing in graph theory that's sort of like a perfect matching, but a little worse, is called a flow. And it's exactly what you think it is. It's kind of the way you should think of a flow is that it's a way to distribute the mass of the vertices in your graph. So I'll tell you what a flow is. So assume you have a mass function from the vertices of your graph to the real numbers. So an n flow phi is, and I'm gonna be a little sloppy with notation here. So it's a function. So your graph is an undirected graph, but the flow is going to take directions on the ends of the graph. So I'll say it's directed on EG, and I'll also say its real value. And it satisfies two properties. So the first, if a flow is moving mass from the pink vertex to the white vertex, then it's moving negative mass from the white vertex to the pink vertex. This is what that direction means. So phi uv is negative phi du for all edges. And the other thing is that it moves the mass of a vertex out of it completely. So if I look at the total flow leaving a vertex, so I look at all of the neighbors of a vertex, and I look at all of the flow that was sent to its neighbors, this should be equal to the mass of U. So the entire mass of U needs to be distributed by the flow among the neighbors. Okay. This is kind of an abstract definition, and it's only really interesting in our context where we have infinite graphs and we can actually move mass off to infinity. So I'm not going to prove this.
Like perfect matchings and fine graphs.
Hmm?
People like flows and perfect matching.
Yeah, they're not. They like bounded flows. They don't quite like a mass distribution flow. Mostly, yeah. Yes, people who do finite graphs love flow. It's they're very useful. And basically, any graph theory problem is just a flow problem. Okay. So I'm not going to tell you how to get an equity composition from a flow, but I will tell you that the goal is to find a flow phi for the mass function, which is the indicator function of A minus the indicator function of B. So this is like sending all of the mass of A to the mass of B. And this is where the fact that A and B have the same measure matters, because this is kind of like a measure zero function in some way. And the reason I left this blank is because not just any flow will do. First of all, it has to be bounded. It can't take an unbounded set of values. And secondly, we need it to correspond to some kind of combinatorial choice of taking paths in here. So if the flow value on an edge is like -0.5, I don't know what that means. So it has to be integer value. And in fact, I'll just take this as a lemma. And this is also due to the original work for Borel circle squaring. So given a bounded integral 1A. Actually, before I do this, I have to do some notation. Okay. Okay. So. We're gonna take a little interlude. So the first half-ish of this talk is specifically about the setting of the torus and circle squaring. But once I tell you how to get from flows to equity compositions, the rest of the talk is going to apply to a sort of more general setup where you have a group acting on a space. So, and more conditions on the group and the space will come up as more theorems come up, but for now, you have a group gamma acting on a space X. So this is a group. This is some topological space, or even just a set, if you like. And you look at some collection of subsets of your space. So open sets, or I don't know, open sets, or rectangles. I don't know. These are the kind of like canonical examples that we're going to look at. You look at some collection of subsets of your space. I already mentioned Boolean combinations earlier, so I can take all possible Boolean combinations of sets in A. All finite Boolean combinations, so union, intersection, complement. But I can also let my group action join the party, and this is going to be, so I'm going to say these are Boolean combinations of translates of A, because we're generally thinking of gamma as like a translation action, but precisely this is Boolean combinations of, the orbit of A under gamma. So, if you start out with rectangles and you take Boolean combinations of rectangles, you get like some rectangle-ish shapes. And then even if you translate rectangles, you still have rectangles. So it makes sense that we actually want to allow more like group action into our complexity. And so one of the key ideas behind testing complexity is that to test if you belong to a set like this, if you live, if you imagine like gamma as corresponding to the graph of your action, you just need to check like a little finite neighborhood around yourself to figure out if you live here, because you're only a finite Boolean combination of sets in A. So if I have a set in here, it's called a local function. Of A, of this class A. And I'm going to use the term local function a lot in this talk. And if I have time, even like show you how you use it as a way to check membership. So this is one of the like key tools to check where something lives in the Borel hierarchy, is to show that it's a local function of something low down in the Borel hierarchy. Okay, and
Local function.
no,
Yeah,
local.
but over here.
Oh, it's the gamma local function.
Sure.
But I'll drop the gamma. I'll drop the gamma a lot. Okay. And the last thing I want to do is define what it means to be a local function of a function. So given a function f from your space of natural, I say A is a local function of f if it's a local function of all of these sets, the inverse images of that. And in the same way, I can go the other way around. I can say, you know, f is a local function of some collection of sets A if every, you know, f inverse n is a local function of this collection of sets A. So I'll go interchangeably between local functions and Boolean combinations of translates. Okay. Two more definitions when we get back to flows. We have to have a delta show up somewhere for complexity. So first a sigma is going to show up. So we have sigma of A is exactly what it was in the Borel hierarchy. It's countable unions. Boolean combination of A. And we can define, you know, sigma sub gamma of A as in the same way. This is just sigma of and delta of A is again like a little lower than sigma of A. So these are sets so that this set and its complement are both in sigma of A. So if you remember the picture, we kind of had like open sets and their complements were closed sets, and then sets that are in both are the delta sets. So this is just a different way of phrasing that, but for, you know, whatever arbitrary collection of sets you want to start with. Okay. So questions about these definitions? Okay. So the statement I want to tell you about how to get from flows to equity compositions, I'll call it a lemma. So if you start with a bounded integral 1a minus 1b flow p, then A is equity composable to B, and the pieces that are local functions so the pieces only depend on the flow, the set A, the set B, and basic open rectangle, where a rectangle is exactly what you think it is, but it might not be axis parallel anymore. Okay, so all we need to do to find an equity composition is find a flow. And there is a way to go. So what the original paper does is construct some kind of sequence of approximate flows that converge uniformly to a real valued flow. And then the rest of it is trying to turn the real valued flow into a bounded integer valued flow. So I'll tell you a little bit about turning real valued flows into integer valued flows, just to convince you that the rest of my talk is nonsense. So from the original paper, we can find a real value bounded real value flow. The definition is hard to parse, so I'm not going to tell you how you get there, but I'll call it P infinity. And the goal is to somehow try to turn this into an integer value flow. And if you do finite graph theory, there are lots of ways to do this. There is something called the integral flow theorem. We'll sort of finite. Which says if phi is a real value m flow for a finite graph G, then there is an integer value, so an integral m flow C that's not too far away from P. So if I look at how much they differ by on every edge, this is the next one. So it's kind of like taking the floor or ceiling on every edge, essentially to turn my real value flow into an integer value flow. So what I want to do is I have the Schreier graph G on my torus, where each, it has a bunch of connected components, uncountably many of them, but each connected component is only countable, right? It looks like a copy of Z to the B. So what I want to do is take a component. I have a real value flow on it. So I draw some finite subgraph on it. And I apply the integral flow. Okay. And then I make it bigger. And I do that in every component. I take a finite subgraph, I apply the integral flow theorem. I take another finite subgraph, I apply the integral flow theorem. And eventually I get a bound of integral flow on it. And this is what left loop is. But this isn't exactly what we can do because you're not guaranteed that when you end up with a flow. You need a way to track the complexity of this. And also when I say choose a place to start in every component, I've automatically used the axiom of choice and I've lost. There's no hope to get anything Borel. So I need a Borel way to start my process and then a Borel way to extend my process. And what I'm going to talk about for the remaining 45-ish minutes is the Borel way to start this process. How do I draw these finite subgraphs on my big, complicated looking graph in a Borel way? One of the other problems that I'll mention is that the connected components themselves have pretty bad Borel complexity. So the orbit of every point is dense in the torus, right? Kind of like how the fractional parts of n alpha are dense in the interval. And I think every connected component is a Boolean combination of G delta sets. So worse than what we want, which is G delta. But if you want to do the proof that came between Marx and Unger and our proof, so the Martineau-Picruco proof, what they use is essentially the complexity of the connected components is what keeps them at delta 0.3 and prevents them from coming down to the delta 0.2. At some point, they have to do some kind of partition across components and the complexity goes up. So we need a way to draw these finite graphs without actually involving the components into our complexity and stuff. Okay, and more notation. So we did a little topology or set theory, and now we're going to do a little graph theory. So, if I have a graph G and a vertex, so the ball or the closed ball of radius Q around X, these are just all of the vertices that are at distance at most Q from X. And I can also define a graph power, so G, what I'll call less than equal to Q, is the graph that has vertex set X. But I connect all the vertices in here. And two vertices are now adjacent in my graph power. In G less than equal to Q, if their distance in the original graph in G was at most Q. So I just, add more, throw in more edges into my graph. And the last thing is the graph boundary, which is notably very distinct from the topological boundary of a set. So for some subset of the vertices, there are two ways I can think about the boundary. I can think about the boundary as vertices inside the set, or I can think about the boundary as vertices outside the set. So the interior boundary, which I'll denote with a partial I of R. These are vertices in R that are adjacent to vertices outside R. I'll draw a picture this way. And the exterior boundary is the opposite, so I'll denote it with a partial O for outside. So the exterior boundary of R is, it's the interior boundary of X minus R. And, another way to think of it is the vertices outside R that are adjacent to vertices inside R. So if I have, I'm not going to draw the edges, I'll have a bunch of points, and let's say this my set R. The interior boundary is, these points. And the exterior boundary is these. Inside and outside. Okay, any questions? So I think the halfway point of circle squaring tops is usually where I hit toast, and that's going to happen again today. So this picture that I drew for you over here is called a toast. I guess if you've never eaten bread before, the way you can think about this is like a slice of toast with some toppings on it. And then there are infinitely many of them, uncountably many of them across the connected component. But a toast is just a fancy or a not very fancy way to say we have finite subgraphs. And there are lots of different definitions of toast in the literature. They all are basically the same definition, but just in different languages. So if you see the word toast somewhere else and it means something else, it probably doesn't. Okay. So the Q toast. And now I'm in the general. Now I am in a general setup of a group acting this way. X. Usually gamma is going to be finitely generated. More conditions will come up by some set S, and G is the Schreiner graph of the action. So exactly what I did for the torus, where you take all of these Cayley graphs and lead to the D. This action is 3. Okay. So we've left circle squaring behind a little bit, and we're in a more general framework now. So a Q toast is a collection of subsets of X. So T1 is the orange sets, T2 is the pink sets, and so on. That satisfy 3 properties. The first is they cover the space. So if remember, the goal is to turn my real value flow into an integer value flow. And if I'm doing this on finite subgraphs, I have to make sure I hit every vertex. This is not always the case for the definition of those. The other is that sort of like saying the connected components of each layer of toast have to be finite, but the Q is going to come in here. So for each n, the connected components of not just the toast Tn, but actually, even if I take the graph power Q, these pieces are valid. So of G of the graph power on Tn, and not just finite, but they have uniformly bounded diameter. So, for each n, there is some dn that bounds the diameter of all of these pieces. And I'll call these the pieces of dn, and these are called the layers of the toast. And so what this first property is saying that, you can't draw bigger and bigger pictures or like bigger and bigger orange pieces in different sets. Or the third property is going to say that different layers of the toast have to interact well with each other. So there needs to be enough space between them. So if I look at layer n and layer m, the distance of the smaller layer from the boundary of the bigger layer is big. So the pieces are not allowed to look like this. They have to, there's a separation that's enforced. If a piece is contained in another piece, it needs to go. Okay. And okay, basically, I'll tell you the kind of so this is technically a corollary of something that was done in the proof in the Perko paper, although they don't state it this way. So coming back to the torus, so we're going to e to the k, d to the b. If the graph has a q toast for, I don't know, some q Tn with every Tn having complexity delta 0 alpha, then I have an equity composition with delta 0 alpha pieces. I'll say delta 0 alpha of A and B. Because if A and B are horribly complex, then they're going to bump up the complexity of the pieces in the equity composition. So the way they get this is some kind of rounding procedure to turn the real valued flow into an integer valued flow that doesn't do worse than what the toast did, but they had a delta 0,3 toast. So their equity composition was delta 0,3. And as you can guess, the key or like contribution is to construct a delta 0,2 toast. So, and I want to tell you which spaces have delta 0,2 toasts, and I believe to do that I have to do more definitions. Yeah. Yes. Okay. We're going to do more definitions. So one thing I will say is that if you remember the picture of the Borel hierarchy, we had open sets, closed sets, and clopen sets. And usually in Euclidean space, we don't have a lot of clopen sets. In fact, we have two. But there are spaces where you have a lot of clopen sets. In fact, you can generate your entire topology using closed sets, and these are called zero-dimensional spaces. And I don't know, like undergraduates probably hate these spaces because they're, they're counterintuitive. How can every set be closed and open? But set theorists love these spaces because the Boolean combination of closed sets is a closed set. And the raw complexity of everything is very nice. And so this work was inspired by a paper of Gao, Jackson, Fona, and Seward, where they construct some low complexity toast, but for zero-dimensional spaces, so spaces that have a basis of closed sets for the topology. And we are going to construct a low complexity toast for pseudo zero-dimensional spaces, where we kind of just try to take the bare minimum of the properties of zero dimensionality that we needed. And now I'm going to throw a bunch of conditions on this group action to tell you what sort of spaces we're looking at. Okay, so our setup is we have gamma, a finitely generated group, and we're going to fix a generating set S. We have gamma acting on X, no conditions so far, with a Schreier graph G, technically G of S. It depends on the choice of generating set. And to construct a toast, we're going to construct something that's not a toast. It's called Borel asymptotic dimension witnesses. These are like, you take a collection of almost toasts that cover your space in a very nice way, and there's not too many of them. So if you're familiar with inductive dimension or other notions of dimension like this is kind of like that. Z to the D should have dimension D and so on. But I'm going to throw some definitions at you for a bit. So fix, I don't know, D and R and N. And in this setup, an asymptotic dimension D witness. So D stands for dimension, and R stands for scale. So this is witnessing asymptotic dimension in our graph at scale R. So what that means is it's witnessing asymptotic dimension in D to the R, basically. So this is a cover of your vertex set by sets, and I'll put the index in the superscript. So U0, DUD. So technically there are D plus one of them, but this is what you need for Z to the D to have dimension D. So U0 to UD, such that almost like, well, actually exactly this condition, right? It's like every set UI is like a partial-ish toast, that there's just one. So the connected components of G to the R restricted UI have bounded diameter. So I've covered my graph by finite subgraphs, essentially. And okay, so another thing, in the case where D is just the Cayley graph of gamma, I'll call the asymptotic dimension of G, or just the asymptotic dimension of gamma. So doesn't depend on the choice of generating set. And I will try to convince you that the asymptotic dimension of Z2 is 2. So, this board is our integer grid, and I'm not going to draw all the points on there. But the idea is we need to find 3 sets that cover the space so that each set only induces like a bounded, or only induces bounded finite subgraphs. So I'll use colors. So I don't know, for my first set, I put some balls that are spaced out around vertices. For my second set, I look at these little corridors between them so the balls aren't too far apart. But then, I have to worry about this other direction when I, go up. So this will be that. I mean, I haven't convinced you that you can't do this with just 2, but at least I've shown you that you can do it with 3. So the asymptotic dimension is at most 2. And of course, we want the sets to look this nice. So in general, we can ask, if I take some collection of sets, can I find, oh, I didn't define asymptotic dimension. Right. So above definition gets, we say asymptotic dimension of the graph G is equal to D if it has asymptotic dimension D witnesses at every scale. Yes.
Okay.
And D is least. So it's the smallest D for which every scale has asymptotic dimension D. And if we take some collection of, nice sets, we can ask, do we have asymptotic dimension D witnesses that are, I don't know, Borel or measurable or whatever? We add a little subscript to this Aston, if A, so this is D, if, it has the asymptotic dimension D witnesses in A at every scale, and D is least. So we can ask, what is the Borel asymptotic dimension? Maybe the asymptotic dimension of Z to the D is D, but the Borel asymptotic dimension is D plus 2 because it needs more sets to actually be Borel. It's not the Borel asymptotic dimension, it's also D in this case, but Z to the D is an M squared. Okay, so as you can see, the asymptotic dimension D, or this definition, is almost giving us a toast. So the idea is, for a toast, you need a sequence. And we can take asymptotic dimension D witnesses for every R. And that gives us a sequence. And somehow, the sequence should turn into a toast because together they cover the space and they have bounded diameter. They just don't interact well with each other. So this is the motivation. And yeah. I will state a theorem badly because I don't want to tell you the general sequence. So this is due to a bunch of people who basically asked, when can you have Clopen asymptotic dimension witnesses for a 0-dimensional space, right? So gamma at x, well, x is 0-dimensional plus the second category Hausdorff, and gamma is a countable group, not necessarily all countable groups. Z to the D, or groups of go. If you're interested in what the full condition is, you can ask me later. It's 3 lines long. I wrote it down because I was worried somebody would ask. Okay, so you have, a nice enough countable group acting on a nice enough zero-dimensional space. Then the asymptotic, the closed asymptotic dimension of X is exactly what it should be. So you can find asymptotic dimension witnesses that cover X with closed sets. And if you mess with this theorem a little bit, you can get something close to Clopen for non-zero dimensional cases. So again, let's say gamma X equals X, and now instead of being zero dimensional, it's a compact Polish space, and pick a basis for its topology. It's compatible with the Polish topology. Then I'm looking for asymptotic dimension witnesses of X, not in open sets, but if you think of these as open sets, then they should be Boolean combinations of them. So Boolean combinations of translates open sets. Okay. It's the same as the asymptotic. Okay. And the whole point of all of this is we want to choose spaces X that have a basis that's somehow compatible with the geometry of the group action. So like rectangles. So I want rectangles where rectangles are defined by a group action to generate a basis for my topology. So maybe in the interest of time, I won't define zero dimensionality for you. But all of the results I'm going to tell you hold for a more general collection of group actions and space than just the torus, but just think of Z to the D. And the torus is like a canonical example of a pseudo zero dimension. So I'll say that X is pseudo zero dimensional. It has a nice.
It draws a picture of like taking that direction on the torus, rectangles, and like where's the topological boundary and the
So okay. Yeah. So okay, maybe I'll draw pictures for you, but I won't define anything. So in a zero dimensional space, a Clopen set is a set that has topologically small boundary, i.e. empty boundary, right? If a set is Clopen, if its boundary is the empty set. And a pseudo Clopen set is a set that has combinatorially small boundary. So if I take this rectangle in my torus, it's pseudo Clopen, because if I look at its topological boundary, and I look at my group action, it only hits the topological boundary finitely many times. Right? This is the topological boundary is a measure zero set, so you expect that it won't hit it a lot if it's a free action. But in fact, it hits it a bounded number of times. I can start at any point and look at its entire orbit and its entire orbit hits this at most n times for some n. Right, when that number is 0, of course, it's an actually clopin set. And when that number is finite, it's a pseudo-clopin set. And a space is pseudo-zero dimensional if it has a basis of pseudo-clopin sets. So hopefully this picture convinces you that the torus with our z to the d action is a pseudo-zero dimensional space. I can take a basis of rectangles that aren't parallel to the direction of translation, which is not how I drew it, but that's a skill issue. Okay.
Maybe it's also worth pointing out that despite being called pseudo-zero dimensional, the property of the action.
Yeah, so yeah, another thing is this is not an inherent property of the space X. It depends on the choice of action on the space X, right? Because it says that so there's like a gamma pseudo zero dimensional hiding here and gamma pseudo clopin, but there are only so many hyphens you can add before a word stops making sense. Okay, but if you forget what these mean, just picture the torus with the z to the d action, and it just means that the boundaries of nice sets are combinatorially small. And the reason we like pseudo-clopin sets is because they kind of behave like clopin sets in the sense that if I take a Boolean combination of clopin sets, it's still clopin, right? Finite unions, intersections. And a Boolean combination of pseudo-clopin sets is still pseudo-clopin. So over here, this is kind of like a clopin asymptotic dimension, right? It says the pseudo-clopin asymptotic dimension of a space is exactly what it should be instead of the clopin asymptotic dimension of a space. Okay, so now I can tell you what our main theorem is. So if we have an action on a space that is pseudo zero dimensional, and I don't know why I wrote this. Okay. Asymptotic dimension of gamma is key. Okay. Well, okay, I don't think you need that part. Okay, then the Schreier graph on X. Let's just forget this. Admits a delta 0 2 tilt.
And you probably want finite, right? That's like.
Yes.
Finite.
Yes. That's what it was. So with finite asymptotic dimension, then this graph has a delta 0 to the Q toast for any Q. Okay. Many people have I lost. I'll close my eyes. Okay, yeah, I have no way of knowing, but for the rest of this talk, I'm going to try to give you like a high level overview of what goes into constructing this delta 0 2 toast and how asymptotic dimension comes into this. So, okay. Okay, so here's an overview of what happens. Step 1 is find your pseudo-clopin asymptotic dimension balance. And step 2, and this isn't going to make sense to you now, but I'll try to make it make sense over the next 15 minutes. So turn these witnesses into almost toast. Step 3. Turn. Almost toast. Into something called a bounded geometry decomposition. I'll tell you more about that. Into a bounded geometry decomposition. And then step 4 is go back. And now, so this is a BGD. And step 4 is turn the BGD into a toast. It's a little convoluted, and I don't have a good explanation for why it has to be this convoluted. It just works out. Okay.
The almost thing seems a little bit misleading. They're too much of the complicated steps out.
Yes, so the almost toast is actually turn them into many almost toasts, I guess. And then there's some stuff that's gonna happen after that. Okay, so let me tell you what we're gonna do at step 2. Okay, I have pseudo-potent asymptotic dimension witnesses at scale 1. Right? So this is the asymptotic dimension witnesses. This is it. Remember scale 1. This is just for the first graph. Power is the graph. I also have pseudo-potent asymptotic dimension witnesses at scale 2. And I have these witnesses for any scale n. And together, each row covers the space. And independently, each set has bounded components. So what I'm going to do is look at the columns of this picture that I brought. To get d different toasts that almost cover the space. So each column is not. So then there's a, I'll say make them toast.
Then
And then it's the column. This is kind of an algorithmic procedure, but what you basically do is you check the toast definitions. You say, oh, if it fails, throw away the parts where it failed, and then just keep doing this. And if everything was chosen nice enough, it's going to work out. So I turned each column into an almost toast, where it's going to satisfy the last 2 toast properties, but each column is not going to cover the space. So what I get is a rainbow toast, actually. Let me actually start this. So, when we turn these sets into toasts, so these, the U01 and U02 have nothing to do with each other to start with. I just had to pick one set at scale 1 and one set at scale 2 to call 0. So these sets are going to change when I toast them into some V sets. Okay. And here, each column, and together they cover the space. And now that I have done some nonsense with the columns, I'm going to do some nonsense with the rows. So right now, all of these toasts, kind of each column itself looks nice, but then they all overlap with each other in different ways. So this is where the rainbow is coming from, where if I imagine that this is, my blue toast looks good, but my red toast sits on top of my blue toast and cuts out some pieces in a way that I don't like. So what I'm going to do is look at this row. And I want to look at the pieces that are cut out by the toasts. So these are the boundaries of the sets, the edge boundaries. I'm going to look at the outside edge boundaries. So these are like the lines that you draw around the pieces of, you know, all of these pieces from here to D. And this is Y1. And I'm going to do this for every row. I'll draw a picture in a second. Yn is the union, so it's the edge boundaries of the different things. So if you have, you know, at some scale, this is your green toast, your pink toast, and your blue toast. Then your Y is just the lines that I drew. And the idea is that these pieces are now a toast. So, you know, the pieces that are cut out by the line. They're not. There are some steps, and they don't have the right complexity. So this is essentially what a bounded geometry decomposition is. I think I'm not going to write out the full stuff. Am I? You know, I'm not going to write it. But so I'll write out a fake definition. So bounded geometry decomposition. So these are a collection of subsets of X is a BGD if three things happen. The first, don't worry about it if you don't know what this is, the Lin suit of the sets is the empty set. So what this means is no point is covered infinitely long. So if you think about the outlines of the rectangles have to keep getting bigger and bigger. So eventually, you know, a point can't be on the boundary of arbitrarily large rows. The second is that if I look at all of the layers after a certain point, they cut out bounded pieces. So the way you should think of a bounded geometry decomposition is that it's almost the complement of the toast. So saying that this cuts out bounded pieces is saying that its complement is bounded by the other. And the third property of a toast is that these pieces are separated from each other, that their boundaries are far apart. This is not quite true for the bounded geometry decomposition, which is why there's a process to turn it into a toast. But what I will say is that not too many boundaries are close. So actually, there is secretly a with constants P and Q hiding here that says like at most, if I look at things that are within Q of my boundary, there's at most P of them, essentially. And it's the same Q and P for all, and which is what's gonna help me post it.
If the P is related to D plus one over here, right? That the close to the overlapping of the boundaries can't happen too much because all of these things have this
Yes.
joint boundary.
Yes. So over here, P is going to be D plus 2. Things can't get too close together. Okay. And You might notice I call these accents, but when I was constructing the boundary geometry decomposition for you, I called them YNs. And it's not just because I'm bad at notation, it's because that's not the boundary geometry decomposition we're going to use to construct a toast. So the idea is that if this cuts out the complement of a toast, then with a little finagling, I can get a toast by looking at its complement. But the problem is that this doesn't have nice enough Borel complexity. I believe its complexity is, I didn't write it down, but it's worse than open. So if I give you a set and I say, I wish this set were an open set, what would you do? And that's exactly what we're gonna do. Oh wait, no, I should I'm leaving this back up here. So we did step 3 or step 2. And actually we want the open sets. So I'm going to define Xn to be the topological interior of Yn. I just turn my sets into open sets, and I hope that they're still a bounded geometry decomposition. So I'll tell you that they are. So Xn, still does cut out a toast. And this is where pseudo zero dimensionality comes in. So the only difference between Xn and Yn is their topological boundaries, but their topological boundaries are combinatorially small. So so whatever action is happening in my graph over here, most of it has to happen in the interior. Not a lot is happening on the boundaries, and this is essentially why going from a set to its interior preserves the bounded geometry property. So checking that this is actually a bounded geometry decomposition is basically exactly the same as checking that this is a bounded geometry decomposition. The only non-trivial step is it still cuts out bounded diameters. You have to make sure that you didn't throw away too much of these rectangles and accidentally get an infinite piece. And the reason you didn't throw away too much is because these rectangles are graph boundaries, but they're very, very small in the topological boundary. So throwing away the topological boundary is not at all throwing away the graph. That's the idea. And then there's some work to turn this into a toast that I'm not going to tell you about. But what I will tell you is that once you have a bounded geometry decomposition with open sets, to turn it into a toast, at each layer you have to do some kind of shrinking process to get these boundaries far away from each other in the next boundaries. So this is some Boolean combination that you're doing, but you also have to care about the next layers that show up. So you're looking at some countable union of layers that show up, which is why when you start with an open set and you start looking at Boolean combinations and then countable unions of that. But then you can stop there. You don't need to go any further. You end up at delta zero. Yeah, and I think I'll stop a minute early. Thank you for coming. Yeah. So, okay, for equidecompositions, yes, if this is the Borel